Hey guys, today's lesson is talking about the reciprocal trigonometric functions. You've learned these as ratios before, but we're going to actually think of them as functions today. Our mindset message for today is that struggling grows your brain. Remember, there's actual research that shows that you get way more brain connections between your neurons when you actually have to struggle to understand something. Now, today's lesson, I would say some of the concepts are going to be a little bit of a struggle to grasp why things connect the way they do. But to actually do the examples and work through things, that might not be quite as hard as actually understanding some of the concepts, which is often the case. So I do encourage you to really try to understand the concepts. It's going to be really good for you. But even if you're still kind of working through why the graphs look the way they do and other things for this lesson, you still can do the assignment and problems and things like that we're going to work on. Our learning goals for today are first to understand the reciprocal trigonometric ratios more deeply as functions. Okay? And the next one is to know the graphs of the reciprocal trig functions. It's not super often or ever you're going to really need to sketch them by hand much, but it is important to know why they look the way they do and the way they behave. Prior knowledge for today would be to know those reciprocal ratios. So cosecant, secant, and cotangent, it's important to remember those as ratios. It's important to remember relationships you've learned when you've studied reciprocals in the past. We'll bring some of that back up. And then there's one thing we're going to do at the end that's going to be helpful to remember information about geometric sequences and series. And I'll add in here, especially when they're convergent. And that's something you would have learned in Algebra 2 course or an advanced algebra course. So let's dive into the very first thing we're going to talk about with these reciprocal ratios today. And by the way, I'm reshooting this portion of the video because I wasn't quite satisfied with the first one. That's why it looked different. And we're going to dive back into the unit circle. And it turns out not just sine, cosine, and tangent, which tangent was itself a kind of surprise, but secant and cosecant and cotangent also have lengths associated in the unit circle. And it's really neat. So let's take a look here. We've already realized that the orange triangles are a very original one, right? Hypotenuse 1, and the literal distance of the bases is cosine theta, and the literal distance of the height is sine theta. Now when we extended this, so the base became equal to the radius, so I labeled that 1. Now don't be, when you're marking this out, make sure you're clear that you know that this 1 doesn't just mean this little piece right here, it means the whole thing. Same with this z, that means the whole base, and this x and that y mean the whole entire hypotenuse, okay? And based on how I've labeled these things, that hypotenuse, and that long base all have, they're going to actually be the lengths of one of those three reciprocal ratios. We did see that this line segment that's tangent, right, this height of the green triangle is literally the length of tangent, right? And the new triangle we made here, we extended it out. The other one we extended so the base equals 1. The new triangle we're going to extend is until the height equals 1. So what we're saying is the top of the unit circle is the exact same height as this, and it stays that way for that purple triangle. So it's interesting because we've seen the hypotenuse for the orange one is 1, the base for the green one is 1, and the height for the purple one is 1. Let's just do some ratios based on the similar triangles then. What should we start out with? How about figuring out what x is? Well, if x is the hypotenuse, I like the idea that the base of the green triangle is 1. So do you agree that x to 1 is the same as hypotenuse to base, 1 over cosine? So we can write that one down. X to 1 equals 1 over cosine theta. But we already know that we've defined that to be secant theta. So it looks like x is secant theta. So I'm going to label that here. Nice. Now let's do y, I guess. I like the idea of using 1 on the bottom like we did x to 1. So what if we did hypotenuse to height this time instead? So y to 1 And let's relate it back to the original triangle again. Hypotenuse to height, oh, 1 over sine. So y to 1 equals 1 over sine theta, which equals cosecant theta. Cool, so this length of this hypotenuse, remember it's the whole hypotenuse, okay, is cosecant theta. And then this right here is the last thing we've got. So base, why don't we do base to 1 again, right? Because this one's purple, so we'll stay in the purple triangle. Base to height. That means that's going to be base to height in the orange one, which is cosine to sine. So z to 1 equals cosine to sine, and we already know that that is the definition of cotangent. Awesome. So that works out. So this whole base is cotangent theta in length. And there we go. We have all 6 of those trig functions as exact lengths of some right triangle associated with the unit circle. I'm going to put up something for you to play with again like I have in the past, like a little applet to see. But I want you to start thinking a little bit about how these behave as this angle changes. For example, if we let theta get smaller and smaller and smaller, if you can imagine this triangle being like this, what's going to happen to this very longest hypotenuse, to the cosecant, because this is going to stay 1, right? So this has to stay 1. It's going to shoot out really far. So the smaller this angle gets, it's going to force that to shoot out really far. And what's happening to cosecant's length? It's getting really long, really fast, right? And as theta gets really close to 0, cosecant actually grows infinitely as it flattens out, right? And what happens when we let theta get up towards 90 degrees? Well, we've already seen that that makes tangent grow infinitely. But how about secant? Well, that's kind of doing the same thing, isn't it? Because if tangent has to connect to secant here, secant's going to grow infinitely as well. So those are the kind of questions and things to kind of think about, because when we study their graphs later in this lesson, you'll be able to kind of connect those things together with what's going on in the unit circle here. So that being said, let's dive into some examples and using the reciprocal ratios and learning about their graphs and that kind of thing. All right, we're going to jump right in. What can we say about the graphs of y equals cosecant x and y equals secant x? And of course, we do know that cosecant is 1 over sine x, and secant x is 1 over cosine x. Again, I'm going to make this comment. I'm not really sure why cosecant's matched with sine. I haven't figured that out yet. And secant is matched with cosine. It's so easy to get those backwards, but oh well. Here's the first thing I want to tell you. First of all, we know that sine x and cosine x both are bound between -1 and 1, right? So they're always oscillating back and forth between those numbers, so that means that's their range. Another way to say this, if you remember what you've learned about absolute value and stuff, usually in Algebra 1, is that the absolute values are less than or equal to 1. That's equivalent to saying this, okay? So I'm going to use the absolute value kind of definition here. There's a fact important about reciprocals. And if you take the reciprocal of a number, and so we're going to specifically say a number n if the absolute value is less than or equal to 1. So what we're saying here is, we know no matter what sine x and cosine x are, they're always between -1 and 1. The reciprocal must be greater than or equal to 1 or less than or equal to -1. And what that means is, the reciprocal of that number is always greater than or equal to 1. Okay, and I know that's kind of a mouthful. You're going to take some time to digest it, but let's look at a practical way of what we mean by this. So if I take, for example, 1 divided by 0.1, okay, so remember, sine x and cosine x are always somewhere between -1 and 1, which means 0.1 could be a value sine or cosine could take on, right? So this represents the reciprocal of some value sine or cosine could be, yeah? 1 divided by 0.1 is equal to 10. I could take other things too. How about 1 divided by 0.2, I guess I could say. Well, that's equal to 5. Even if I did 1 divided by 0.9, that's equal to 1.1 repeating. No matter what, watch what happens. if I take 1 divided by something less than 1, or between 0 and 1, it's always going to give me something out that is bigger than 1. Even this, as it gets closer to 1, right? 0.9 is pretty close to 1. The output's always going to be still something bigger than 1. So that's what this is saying right here. The reciprocal output's always going to be greater than or equal to 1. Now, it's or equal to because technically speaking, if I just did 1 over 1, that's exactly equal to 1, right? So if the function, sine or cosine, actually reaches its maximum or minimum actually, at 1, then that ratio is just stays 1. Now, the cool thing is this could be plus or minus, because we realized it could also go down to negative 1. So that just results in something plus or minus 10, and that's where this absolute value comes into play, or this piece of it. Okay, so this fact holds true, and what that means for us is, if you were to look at the graphs of secant and cosecant, their range is exactly the complement or the opposite of what sine and cosine range is. So since sine and cosine both actually go between negative 1 and 1, secant and cosecant actually stay exactly outside of that. So we're going to take a look at the actual graphs and what they look like, and you'll see what we mean. Alright, so we can actually jump into learning what the graphs are going to look like. First we got to talk about asymptotes. Just like with tangent, since these are ratios, anything that makes the bottom equal 0 is going to create an asymptote. Remember, that means it's an imaginary like boundary or border that it doesn't cross over. So here's what we got. For cosecant, the asymptotes will clearly be whenever sine x equals 0, and that's just multiples of pi, right? So I've labeled those already on here on the multiples of pi. It's very helpful to have the sine graph actually graphed if you're going to sketch this by hand, because there's a nice relationship between cosecant and sine. Remember how we said cosecant is always going to be bigger than 1 or less than negative 1. Here's how these graphs relate. They're going to have the same maxes and mins as each other, except the cosecant in each of these sections is going to look kind of like a U like this as it comes around and approaches the asymptote. And then here it's going to be upside down. So here's this, etc. And the cool thing is, same deal happens. The asymptotes for secant are going to be whenever cosine x equals 0, and the way the shape of the graph looks is exactly identical to the other one, but it's just shifted. It's also important to note that these graphs are also periodic. They're periodic, they repeat after actually the same amount of space as its related graph repeats. So this achieves 1, 2, that forms a whole period within the span of 2 pi. And the same here, it repeats the top and bottom piece within the span of 2 pi. So these still have a period of 2 pi, just like sine and cosine. So if you imagine just erasing the cosine curve and the sine curve here, the purple that's remaining is the graph of cosecant or secant. Let's take a look at cotangent a little bit now, and then do a few examples to wrap up. So let's wrap up everything we've learned about secant and cosecant, and luckily cotangent's a really quick conversation. So we know that because sine x and cosine x both have absolute value less than or equal to 1, remember that just means they're bounded between negative 1 and positive 1. This means that their reciprocal functions, their absolute values, are greater than or equal to 1. So they have the exact complementary outside range. Their asymptotes occur for cosecant when sine x equals 0, secant when cosine x equals 0. And that tells us everything about their graphs. We looked at those graphs. Now let's jump to cotangent. Nicely for us, tangent, the original tangent, has an unrestricted range. So when we do this reciprocal thing like we talked about, cotangent is also going to have an unrestricted range. That's really nice. So the only thing left for us to do is to talk about their asymptotes and look at their graphs. Well, cotangent, on the bottom of him is sine x, instead of tangent, on the bottom was cosine x. So instead of when cosine x equals 0, cotangent asymptotes will happen when sine x equals 0, and that happens at multiples of pi. So let's actually compare the two. This is the graph for y equals tangent x, and this is familiar to us. And there's where its asymptotes are and all that business. And go ahead and take a look at the graph of cotangent x. They look very similar, right? They have different asymptotes because they have a different function on the bottom, but their shape is identical except tangents pieces are increasing and cotangents are decreasing. I'll leave that to you to figure out or think through a little bit more of why. It has to do with how the sine and cosine relate to each other. It might even help to actually look at the graphs of sine and cosine together. But that's not a conversation we'll have. If you'd like, you can explore that on your own a little bit. So we're done wrapping up everything about these things. There's just like one or two things I want to look at a little further example-wise before we're done with today's lesson. Okay, so I forgot to label the tangent piece of our last thing, number 2, so we'll call this 3. So this lesson's largely informational. The only real thing worth thinking about, I think, as far as like looking at specific examples to do would be like solving equations involving these things. So find all solutions to the equations. Again, we're just on 0 to 2 pi. So how might we tackle this? Well, remember, it's always good to relate it to something you are familiar with, right? If I'm asking about secant here, well, let's relate it to what we know about secant. Cosine, right? If I'm asking when does secant x equal -2, that's the same as asking when does cosine x equal -1/2. Right? Because they're the reciprocal of each other. So if I reciprocate this to get cosine, then I must reciprocate this to get that. Aha! Now we know exactly how to finish solving that, right? So I want you to pause right now and attempt to finish the remainder of these yourself, and then we'll look at them together. Alright, we didn't actually finish solving this yet, so let's finish solving this. When is cosine equal to -1/2? That's going to be at 2 pi thirds or 4 pi thirds. 2 pi thirds or 4 pi thirds. For B, it says when is cotangent equal to √3? Well, remember that's the same as saying when is tangent x equal to 1/√3. This one's a little trickier because it might be like, wait a minute, how did I get 1/√3 with tangent? I want you to remember that tangent is sine over cosine, and 1/2 and √3/2 are a pair that you'll find on the unit circle together. And when you take those, the 2's cancel out and you get 1/√3, right? So it's kind of a loaded one, this one. It's not quite so simple as A. But where is sine 1/2 and cosine √3/2? That's really what this is asking, right? And it seems like there's only one spot that's going to make that exactly the same. Well, actually, hold on. This could be minus and minus, couldn't it? So there's 2 spots, somewhere in quadrant 1 and somewhere in quadrant 3. So where is cosine √3/2 and sine 1/2? That's going to be, I think, at pi/6. Yeah, pi/6. And the other one's going to be the negative version, right? So we have x equals pi/6, and the negative version is going to happen at 6/7 pi/6. Yep. So pi/6 and 7 pi/6 would be the 2 solutions for that. Let's take a look at this. Now you can look at this right away, and if you think about what we talked about with its range, you might have a red flag come up already. Or if you tried to reciprocate it and say, oh, well, this is saying when is sine x equal, well, what's 0's reciprocal? 1/0? Right? Doesn't make any sense. But we remember that this can't even reach 0 anyway. So our conclusion here is that there is no solution to this guy here. All right? And D, cosecant squared equals 1. How do I undo a square, right? Okay, square root. The only thing I'm going to warn you about is don't lose the fact that there's 2 possible solutions, because this means that cosecant x equals either plus or minus 1, right? And again, if we do the reciprocal, that means the reciprocal of cosecant is sine, so this means sine x equals, what's this guy's reciprocal? Oh, that's nice, it's just plus or minus 1 still. So we're really looking for where sine x is equal to plus or minus 1. Well, that's going to happen at pi/2 or 3 pi/2. Pi/2 or 3 pi/2. Okay, so there's various equations that that are good to think about for these. And one last example, which is what I told you earlier, that relates to geometric sequences and series, that's quite interesting and relates to calculus a lot.